Everything that tangibly exists in this universe is known as matter. Before I started teaching biology, if you asked me what matter was, I probably wouldn't have had a good definition. Um, so, what does that mean, matter, right? Can I hold it in my hand? Can I breathe it in? What is that? Matter, its basic definition is that it has mass, so it takes up space, and it has a state of charge. So I'm sure that you are thinking, oh, it could be positively or negatively charged. But there's a third option there. There's the state of having no charge. So matter is capable of having mass and having a state of charge. So there are these things, these types of matter called oxygen, carbon, nitrogen, and all of the other elemental identities that are listed here on an abbreviated version of the periodic table of elements. Usually, this is the point where some students ask, wait, what's an atom? How about a molecule? When do they come into play? Soon. In this class, we're going to come to know the abbreviations for many of these elements. Some of them are intuitive, such as oxygen, hydrogen, carbon, but some of the abbreviations refer to the Latin root word. The prefix nature, well, there's a couple of them actually, that's just one, stands for sodium. And so we use the abbreviation Na for sodium. The prefix cal, starting with a K, stands for potassium. And therefore we give potassium the K abbreviation, which is often confused for calci, which, where's calcium? Well, wherever calcium, oh, there, right there. Sorry. Often confused for calcium, whose abbreviation is Ca. So notice how the second letter of each abbreviation is always in lowercase. The numbers that you see here are called atomic numbers, and these all indicate something about electrons or the structure of these things. We'll just leave it as that at that for now. An atom is the smallest packet of matter that we know of. Actually, that's not exactly true. We believe that there are smaller structures called subatomic particles, but we've never actually viewed one of these with the technology that we have. The subatomic, so we display a shadow and kind of look at the shadow. So subatomic particles, there are three types of them. There are protons, and I'm going to use some abbreviations here that you can use in your notes as well. There are protons that are positively charged, neutrons with no charge, and electrons that are negatively charged. It's important for us to understand that all these subatomic particles have these different charges, but it's even more important for us to note their different locations in the structure of an atom. And so this is the first anatomy that we're really doing. Neutrons are uncharged, not negatively, and they exist in the juicy center of an atom, which is called the nucleus, which is a word that just means center. Trapped in the nucleus with them are protons, which are positively charged. Protons and neutrons never leave the nucleus. If a proton tries to leave, there's a big explosion, and movies like The Hills Have Eyes. What? The number of protons an atom has, it depends on which of those elements it is. It depends on its identity. So the atomic number of the element that the atom is tells you how many protons an atom of that element will have. For example, hydrogen has 1 proton because its atomic number is 1. Oxygen has 8 protons because its atomic number is 8. Sodium has 11. Right? So in both of these diagrams here, and these are both diagrams of a carbon atom, there are 6 protons and 6 neutrons trapped in the nuclei. You go ahead. You can count them. Go right ahead. The negatively charged electrons, they are not in a fixed location. They move around, they fly around. And so we get this like kind of cloud as to where they are. The diagram on the left is called a planar model of a carbon atom. But the diagram on the right is, well, it's my interpretation, but it's a little bit more accurate that the electrons fly around, creating a cloud of orbits, of pathways, of things that are actually called shells. So why don't the electrons fly away, right? Because each electron is attracted to each proton in the nucleus. Positive and negative attract. So we're talking about atoms on this slide, and it's important for us to realize that an atom, by definition, has the same number of protons that it has of electrons, and that dictates that an atom, by definition, has no charge. Electrons don't just fly around the nucleus randomly. In fact, an atom is much like a peanut M&M. The peanut is the nucleus, and it's dipped into chocolate to make a shell that dries. And then you dip it again to make a shell that dries. And then you dip it again, dip it again. So these planar models are in 2D, and you have to think of the real structure in 3D. For example, electrons do not orbit the nucleus in a predetermined path like the planets orbit around the sun, right? So an electron would have almost an infinite number of orbits around the nucleus, forming a shell or a cloud. And we call these areas shells, and shells hold different numbers of electrons. So the circular lines in these drawings here are shells. Before we even get started looking at valence shells, you should know two preferences of the universe. Shells like to be full, and electrons, they like to be in pairs. The first shell for any and every atom in the entire world holds only 2 electrons. It can hold 2 electrons. And you can see in these diagrams on the right and on the left that yes, which this is oxygen here, and this is carbon. And yes, there are 2 electrons in the first shell of each of these atoms. Let's just look at those 2 for now. And I'm sorry, we know these are atoms because the number of protons in each of their nuclei is equal to their number of electrons. And again, if you want to count them, I'll wait. So as we draw these planar models, we put the protons and neutrons in the nucleus lockdown. We draw a line representing the first shell of that chocolate that covers the juicy nucleus, and we put 2 electrons flying around in infinite orbits in that shell. This is good. The first shell is full. The electrons are paired. Good. Let's move to the second shell, which can hold 8 electrons, but it's only going to hold as many electrons as it needs to because we're going to go by the atomic number. Oxygen's atomic number is 8, and so we would draw only the remaining 6 into the second shell. This valence shell is not full, and that is bad. Oxygen could give away these 6 electrons, but have you ever tried to rehome a litter of stray cats? I dare you to find 6 people that'll take a cat. It's way much easier for oxygen here to find 2 other atoms, or even one wanting to donate 2 electrons, than it would be to try to find structures to take 6 of them. So now take a look at carbon on the right and apply the same rules. Carbon's atomic number is 6. So we put 2 electrons in the first shell, and the rest go into the second shell. This time we have 4 out of the 8 total electrons the shell can take. So carbon potentially could bond with 4 other items, right? It could take on 4 bonds bonding to 4 other things. Okay, so these outermost shells are called the valence shells, and they're important because these are the only shells that can donate, accept, or share electrons, right? And they can donate, accept, and share to try to get their shells to be full and get their electrons in pairs. The middle atom here of hydrogen kind of defies all of the rules, all of the things I just told you, but it defies all expectations. This lonely electron here is in the outermost or valence shell. And unfortunately for the lonely proton in the nucleus, literally everything else in the world has as many or more protons. And so this electron is constantly attracted to anything but its original proton. So hydrogen atoms are kind of a rarity. They usually exist as another type of structure that we'll talk about. An ion is an atom that has lost or gained electrons from its valence shell. By doing so, we get positively charged and negatively charged structures. That's what an ion is. Don't be fooled that you can make an ion by gaining or losing a proton. You can't. Remember, big explosion, radiation sickness, bad B horror movies. The planar model on the left is a sodium atom, and its atomic number is 11, so it has 11 protons, 11 electrons. 2 electrons go in the first shell, 8 electrons go in the second shell, and then we have this lonely electron all by itself in the third shell. And this is bad because shells like to be full and electrons like to be paired. Sodium would like to give this electron away. And if it does, the second shell, which is full, becomes its valence shell, and that satisfies our rules. The planar model on the right is a chlorine atom, and its atomic number is 17. To make a long story short, it has 7 electrons in its valence shell, and the shell can hold 8. So this is almost like a match made in heaven here. Sodium has 1 extra electron, and chlorine wants 1 electron, and this is how a salt is formed. A sodium atom donates an electron to a chlorine atom. The sodium atom then becomes a cation because now it has 1 excess proton. Our chlorine atom now becomes the chloride anion because it has 1 more electron than proton. It's really all about the outer shell. It determines the ability of an atom to make bonds with other atoms, molecules, compounds, and a whole bunch of other nouns you learn in chemistry. But by trying to fulfill those 2 rules, this is how bonds are made and bonds are broken. Ions are formed, right? This is what's happening inside of you right now. You're just a bubbling cauldron of electrons. In my general biology class, we talk about ions, but here in anatomy and physiology, we extend that a little bit and talk about them as electrolytes. It's important to realize that you have electricity running through your body, and the current has a very easy time doing that because you are a water-based organism. So a thought is really just the movement of electricity. If you move your big toe, electricity just zapped through your spine, down the sciatic nerve, to bring the message to your toe muscles that they should contract. And that electricity that your body uses to move around information, it depends on the ions that are present in your blood. It depends on what is called your interstitial fluids, right? The fluids between your cells and your cells themselves. Therefore, we call all salts electrolytes, which is a word that denotes the ability to conduct an electrical current. So I guess you could say all ions are electrolytes, but not all electrolytes are ions. When a salt is absorbed into your blood, which is a water-based substance from your small intestine, it immediately breaks apart into its corresponding anion and cation. So the salt you ingested at lunch immediately split into the sodium cation and the chloride anion when it hit your blood. This splitting is called dissociation. That is what you see in the flask down here on the bottom. The cations and anions are fully separated with that strong electrolyte. Cations and anions in a weak electrolyte also separate, but not all of them. So as you can see in the picture, weak electrolytes don't dissociate completely in your blood. Anything that isn't an electrolyte doesn't dissociate. The molecule in the flask on the left, it could be an alcohol or something, which stays fully intact when you put it into water. It is a non-electrolyte. It does not contribute to the conduction of that electric current.